Welcome everybody for today's webinar regarding dual-comb spectroscopy at high resolution for gas mixture studies. My name is Florian Eigenmann and I'm your host today, giving some updates on the technology, specifically the first 15 minutes. And with me on the panel is Muriel Lepere. Muriel is a full professor at the University of Namur. She was also education vice rector previously from 2013 to 2017. Muriel is also on the board of several academic committees. For example, at the University of Namur, Academic Pole of Namur, Open University of French Community, Société Scientifique de Bruxelles, and her background is physicist. She received her PhD at Paris Sud. Thanks, and Muriel, please go ahead.
Florian. Hello, everybody, and thanks, Florian. This is a great pleasure for me to present Florian Eigenmann. He's a chemical engineer. He obtained in 2005 his PhD from ETH Zurich. And after that, he works in several private companies as broker, where he was responsible of development for a near-infrared spectroscopy. After that, he worked at Toledo, Metlev Toledo company, and since almost 2 years, he's sales manager at RSF.
Thanks for the introduction as well. The outline for today is specifically first the benefits of dual-comb spectroscopy, speed, brightness, higher resolution, then but also a few words specifically about rapid and step sweeping from dual-comb spectroscopy. As you have heard, another webinar like 2 weeks ago from Michele et al. And then I will go over some other applications and then head over after 15 minutes to Muriel Lepere. We have a Q&A session at the end, probably roughly around 45 minutes from now. So what are the benefits from the RSF1 or from dual-comb spectroscopy in general? So there is actually several ones besides speed, which we have seen in previous applications. We do have, for example, here biospectroscopy in speed or shock tube analysis, which requires really fast time scales down to the microseconds or millisecond time range. There's also a possibility, as I said, high resolution, which was reported earlier from Michele et al. In optics, and it was actually published in Optics Express. Brightness, that's a big advantage of this technology as well. So the brightness is not just like the speed as you have on the x-axis. On the y-axis, you have, instead of a glow bar source, which are used typically in FTIR spectrometer, we do have lasers. And like this, you have a lot of photons at the given spot. Then you have another advantage, like compared to other laser spectrometers, you have a broadness of 60 to 100 wave numbers. This is the parallel multi-wavelengths advantage, where you have the light where it's needed. So that's a huge advantage, and I will come a little bit on that point later on. So the dual-comb spectrometer, how it looks like, I could go quickly over the technique. There are two frequency combs. Those beams are mixed on a beam splitter and detected on a high bandwidth MCD detector. So each pair of these optical modes produces a radio frequency beat note. And this frequency spectrum can be measured with conventional electronics and represents the optical spectrum. So each comb tooth produces a delta F-rep signal, and with each comb tooth from the second laser. So with this delta F-rep, which is typically in the order of 1 to 5 megahertz, we can choose the signal between F-rep1 and F-rep2. So I come a little bit to that later, specifically in step sweeping and rapid sweeping. So what you get is a heterodyne signal. I put in ones like a water vapor band from Hydron, because that's a laser around 1650, which we primarily use for biospectroscopy people to measure the MI1 band. And you have a lot of lines at this time is the point spacing of 0.3, and you see the broadness more than 60 wave numbers, roughly 200 lines. Earlier, this was reported again from EMPA in Switzerland. This rapid sweeping just 2 weeks ago, the webinar, and also I presented a few first results in Dijon last year. So this is a very fast technique, and I will explain that in the coming animation which we just did. So you have the possibility here, or that we really use that both lasers are swept together. So you have two lasers. One laser is going through the sample compartment, and the other bypasses the sample compartment. And like this, you sweep both lasers over the entire range, and you fill all these gaps, and you get to a really high spectral resolution. So the amplitude information is there, but you have a loss of an exact frequency axis. So there is also a really huge advantage. There's a very fast acquisition, previously reported 120 milliseconds, but you can do that even faster, down to 6 milliseconds for the entire spectrum. And the disadvantage is that the frequency axis is unknown, and there you have a certain uncertainty. So you have an uncertainty in the wave number step. So let's go and introduce now the step sweeping, because that was used later for the measurements which Muriel will present. So here, that's actually the reason why it's step. We have in the first step only a change of the current on sample laser. Just on one laser, we change the current. Sorry, I should not rush too much through that. And then you see this in the optical frequency. You only sweep the laser here, one laser, the red one in the animation on the top. And then you react exact tuning of the sample laser in the heterodyne. And there we can measure that in the radio frequency with better than 1 megahertz. This gets an exact frequency between all measurement points. So I go through the animation as well, because here then you have the second laser, which is not going through the sample. We call it here the oscillator laser. And we bring back the heterodyne lines to the original frequency. Just like this, step by step. So there's an advantage still. One advantage compared, for example, to the rapid sweeping is that we have an exact point spacing. This is known during the sweep, and it's still very fast. So currently we have measurements better than 10 minutes for an SNR of 500, but we are very confident that we can increase that as long as we speak. So you see, that's why we call that step sweeping. An animation which I just got recently from marketing. I really like that a lot. It explains a little bit, or it shows how we fill this high resolution data between the point spacing. When you read such publications, you see a little bit the difference between point spacing and resolution. What I previously got from one of our former champions, I would say, I'm also very happy that he's also in the audience, Martin Koch. He had one of the highest resolution, I think it's the highest resolution FTIR scanning spectrometer with an MOPD, maximal optical path difference, of 11.7 meters. And he gets actually a resolution of 5 times 10 to the minus 4 wave numbers. But you see here also a little bit the dimensions. Such a spectrometer is roughly, I mean, if you have the maximum optical path difference of 11.7 meter, is roughly 12 or 13 meters long. So here you get actually the dimensions of the RSF1 with an optical resolution of 0.0001. So that's a benchtop spectrometer. So currently, we're very confident that we get to the same or even better resolution with this spectrometer. Other examples, you have I was talking a little bit about the broadness. You have the possibility to measure 60 wave numbers, and the system is designed that you can exchange those laser modules. So the laser modules can be exchanged very fast, and then you can measure after stabilization at another wave number. So here you have the lasers which we already have currently in stock. And I highlighted one, the 1300 laser, because for the next methane measurements, they were already taken at 1300. And you see we have other lasers at 1650 for biopeople, or previously reported at 1200. Also these methane measurements, which were recorded by Janella, Lucas Emenek et al. Quick overview about all the applications where we have spectrometers so far in the field. So we work with other users together there for protein dynamics. There's another webinar coming up in a week from Joachim Heberle, and Markus Mangold will assist that as well, where he does such folding, unfolding of proteins and peptides, specifically for reactions which are non-reproducible. Then combustion diagnostics, another field where you need very fast spectrometers, where you need the speed, and because you don't have movable mirrors, movable parts at all, you can go down to the microsecond time resolution. And another application where we recorded previously also in a webinar is stopped flow and microfluidics. You can do this rapid scan. It's not really rapid scan because it's as I said, no movable parts at all, but you can do that continuously for 220 spectra per second or even more, but most of the case 220 spectra per second is good enough. Then Ian Burgess just had a webinar about rapid monitoring of electrochemical reaction, so it's spectroelectrochemistry. There's a paper out there as well, so I will not go in details here. So and now coming to high resolution spectroscopy. High resolution spectroscopy, if you want to see more information or other results on the first methane data taken at 1200, you can do so. You find the recordings on our webpage from IMPA. And then now the next few slides I will hand over to Muriel Lepere. Before I do that, there's an animation or just like a movie from the lab, how we took, that you have a little bit of information how such a spectrometer looks like. You see here also the methane bottle connected, and I just let that run. And then I will hand over to Muriel.
Thank you.
Muriel.
Yeah. Thank you. Okay. Hello, everybody. During the next minute, I would like to talk about why I choose to acquire RSF1 and what is, in fact, the interest of my team for such instrument. You see here a picture of RSF1 at R-sweep with our cell, but I will talk later. Briefly, I would like to remind you some molecular spectroscopy in gas phase. Such spectroscopy is both fundamental and applied interest. For the fundamental point of view, this study allows to understand the inter and intramolecular interactions in gas phase. But also, in fact, for applied point of view, results of molecular spectroscopy, in particular line parameters, are required to study atmosphere, in particular planetary atmosphere, but also our atmosphere, and to study thus the pollutants in our atmosphere, for example, the gas, the residual gas of combustion. In fact, in absorption spectroscopy, we study the transmitted light through a cell with a gas mixture. And if you look at the transition between two row vibrational levels, we obtain no a peak, just a monochromatic line, but a line with an intensity, a width, and something like a profile, in fact, a line shape for each line. In atmosphere, we do not know the composition, the concentration, and the temperature. But we know this data in laboratory. Such way, with experimental or theoretical spectra in laboratory, we are able to determine the line parameters as line intensity, line broadening, pressure shifts, etc. These data are used after by atmospherists for the inversion of atmospheric spectra. Such way, they are able to determine composition, concentrations, and temperature of different atmospheres. For that, for the works realized by atmospherists, they need to have very accurate line parameters. Indeed, recently, several studies have put in evidence that the precision of vertical profile of concentrations in the atmospheres are directly dependent on the accuracy of the line parameters. Thus, we have to produce a lot of line parameters for different gas mixtures. For that, we have thus to obtain accurate spectral line parameters for different gas mixtures, including nitrogen for our atmosphere, but also other perturbers as CO2 for planetary atmospheres. We have to obtain a lot of absorption lines, to measure a lot of absorption lines, and we have to make these measurements in different conditions of pressure and temperature. For that, we have two solutions. Make a theoretical calculations or a precise measurement. In fact, both are needed. Calculations based on state-of-the-art models allow to have a large set of accurate data. But these calculations need measurements, accurate measurements to validate, for example, the intermolecular potentials. It's the reason why measurements for a lot of absorption lines with different gas mixtures and various experimental conditions are required, and thus very good spectrometers. Very good, that means large spectral range, high resolution, and excellent signal-to-noise ratio. Since a long time, Fourier transform spectroscopy is a technique that a lot of teams everywhere in the world used to do such work. Here is an example of results that I have obtained a few years ago in Paris with a homemade Fourier transform spectrometer with a very good resolution, but only about 10 to the minus 3 wave numbers, and a signal-to-noise ratio of about 500. This study was devoted to line profile, study of water vapor diluted in nitrogen, very interesting for our atmosphere. Another example of spectroscopic study, this example is a study that we have realized in my team in Namur, devoted to pressure shift of lines in the nutriband of methane diluted in nitrogen. We have recorded spectra with a 2 beams diode laser spectrometer. The apparatus function was excellent, about 10 to the minus 5 wave numbers, with an excellent signal-to-noise ratio about 2000 or more. Thus, if we compare a Fourier transform spectroscopy and tunable diode laser spectroscopy, or in general, laser-based spectroscopies, you can compare two things. A forest, you see a forest with a Fourier transform spectrometer, and you see just a tree, but in details, with a laser-based spectroscopy. Here is an example of results that we have obtained with my colleagues in Brussels, in Belgium, with a Bruker Fourier transform spectroscopimeter, sorry. This study was devoted to line intensity measurement of formaldehyde. You see here the FTIR spectrum, and just a spectrum obtained with a diode laser spectrometer. The spectral range is totally different, but the precision, the resolution of the spectrometer, the signal-to-noise ratio are also different. If I compare Fourier transform spectrometer with laser-based spectrometers, is diode laser or quantum cascade laser spectrometers, we see and we know that with laser-based spectrometer, we have an excellent resolution, about 10 to the minus 4, even 10 to the minus 5 wave numbers, with an excellent signal-to-noise ratio, 1000 and even more for QCL spectrometer. But we have only very small, very narrow spectral ranges, 1 or 2 wave numbers for diode laser and 5 to 10 wave numbers for QCL. And the time of acquisition of a spectrum is very short with these techniques, only a few seconds, 10 seconds. With FTIR, the resolution is good, but less good. The signal-to-noise ratio is good also, but the main advantage is the spectral range, which is very, very large. But for that, the time necessary to record a spectrum is very large too, often more than 4 hours. I would like now briefly present some results that we obtained with my team in Namur. Here's a nice picture, not the Lake of Zurich, only our 2 rivers in Namur with the beautiful citadel built by a French guy, Vauban. In my team, we study individual line profiles, but also individual line parameters as wave numbers, intensities, collisional broadenings, pressure shifts, or line mixings, for example. For that, we have different equipments, different devices, diode laser and QCL spectrometers, but also different absorption cells with optical path length varying from a few millimeters to 120 meters. Sorry. We have also developed ourselves low and high temperature absorption cells with different optical path lengths. And very recently, we have acquired RSF for new projects and new measurements. Here you see 2 photos. The first one on the left is the diode laser spectrometer. The diode laser is being purchased by Laser, and the second one, the QCL spectrometer, with the QCL provided by Laser. These 2 spectrometers have excellent resolution and excellent signal-to-noise ratio. Here is a photo of RSF, not yet in Namur, because we will receive the spectrometer, in fact, in a few weeks. But we have begun the collaboration with RSF, and the first measurements have been realized at RSF with just 1 cell, a cell of my team. On the right picture, you see RSF with all cell inside on the right part, and on the left part of the spectrometer, you see the laser module. You see also that the size of such spectrometer is very small and it's convenient for a lot of work in our laboratories. Here is our cell inside RSF1. We can also make measurements with cell with external cell, but in this case, this cell was perfect for the measurements that we plan to do and that we have to do. And here I would like to present briefly homemade absorption cell developed in my laboratory. We have just developed absorption cell for measurements of collisional parameters at low temperature, quite 100 kelvins, and other for high temperature until 1000 Kelvin. These cells allow to make measurements with a very good temperature stability, with a gradient of temperature and with different optical path length varying from a few centimeters to 10 meters. Here is an example of QCL Spectra that we have obtained recently about CH3Cl diluted in nitrogen at low temperature. For each study, we record spectra in different conditions of pressure, as you can see here. And such way, we are able to determine the collisional or the line parameters or collisional parameters with a great precision. In fact, for each line at each pressure and each temperature, we adjust a line profile, a theoretical line profile. You know probably the void profile, which is very well adapted to line parameters, but due to the very good resolution, the excellent resolution of new spectrometers as RSF1 and the excellent Signaltonoise ratio, actually we are able to put in evidence that void profile is not the best profile to measure line parameters, because we can put in evidence fine physical effects that occur in gas phase, in gas mixtures. And for that, we have different line profile. We see here Russian and Galatry, but I think that actually the best profile is the profile developed by Hartmann-Tran, and I hope that due to RSF1, we will be able to prove that this profile is probably the best profile to describe an absorption line in infrared. From these fits, we are able, for example, to determine the width of the line. It was the case here about a line of methane dilated in nitrogen at low temperature. And if we plot the collisional width versus the pressure of the perturber, you see such a graph, and we are able to make a linear regression, and the slope of the best straight line gives, in fact, the collisional broadening coefficient. And this coefficient can be put in international database as hydrogen. You can imagine that if you have to do such thing for each line, and if you have to make measurements with a diode laser spectrometer, thus you have to make a lot of spectra. It's a long time of work, in fact. Okay, and it's a pleasure now to present the first experimental, in fact, spectra recorded with RSF1 at high resolution, in fact, at 10⁻³ wave numbers. And we have recorded, not we, my colleagues at RS3, the team of RS3 has recorded this spectrum. This is a very large spectrum for me, because I'm a laser specialist. It is a 60 wave number spectrum recorded at high resolution of methane. We compare this on this figure. We compare this spectrum with hydrogen simulation given by the parameters of this database. And if we make a zoom of a small part of this spectrum, you see here with more details, just some wave numbers. And you see the very good agreement between hydrogen simulation and our measurement with RSF1. And I would like to make a zoom, a second zoom on just on two, lines. And you see here the excellent signal-to-noise ratio and agreement with hydrogen database. And you see the resolution of the spectrometer. And yes, we are happy to obtain such spectrum. It was one of the first, for me the first, but okay. And here we can also check another part of the first spectrum presented today. Here is a part at near 1295 wave numbers. And you see always the same agreement on, between hydrogen and our measurement, and also the excellent signal-to-noise ratio and the resolution. You see the different dots, the point of measurements, in fact. Not the points, sorry, but as Florian has very well explained today, thus I'm not yet a specialist of dual-comb spectroscopy, as you remark. If I, to finish my talk, I would like to present this table for the second time and add RSF1. RSF1, the resolution is probably better than 10 to the -3 wave numbers. And the signal-to-noise ratio for an acquisition time of 10 minutes is quite similar to a Fourier transform spectrometer, thus 500. But if we compare RSF1 with laser-based spectroscopies, you have here 60, at least 60 wave numbers of spectral range. And it's wonderful for new measurements, new projects of my team, sorry. And to finish, I would like to thank all the members of my team who have participated to the slides that I've presented today, and also my main financial supports. And to finish, it's a great pleasure to thank especially all the team of RSF, sorry, especially the three co-founders, Andreas, Marcus, and Marcus, and the team, the application and research and development team at RSF, Raphael, Pete, Marcel, and Kuno. And to finish, I would like especially say thank you, Florian, for your support and for all the job, all the work that we have made together. Sorry. Thank you, Florian.
Thanks, Muriel. I will open now the Q&A session. Thanks for this excellent talk, and please use the button at the bottom. We got already several questions, and we will address them specifically. If it's more the technical part, then I will cover that. I have also the CTO of RSF close by. He will probably step in at one point, but I hope to handle one of them directly, and Muriel specifically for the application questions. To kick off the session, I have already a few questions. Specifically here, the time-dependent, the signal-to-noise time-dependent question. One of the questions was actually, does increase the recording, or does it increase the recording, or does it improve the signal-to-noise ratio? Do you do a scan accumulation and an average? Yes, of course, the longer you scan, that's like with every spectrometer, the better the signal-to-noise will get. Currently, we perform measurements with roughly 10 minutes acquisition time to achieve those nice results of 0.001 wave number resolution with 500 SNR. But of course, when you scan longer, it goes also here with the square root. So if you increase the measurement time to 40 minutes, you can expect an SNR of 1000. Then there is another question who come in. How far can you push the resolution of this technique? That's also something we have already an answer here. It looks like this is a very important part. How far can you go for the resolution? And of course, obviously, I had a discussion before with the technical team. So you have the possibility with that spectrometer of the RSF1 to go to 1 to the times 10 to the minus 4 wave numbers, which is outstanding. That would open a lot of new applications as well. Previously, we got some questions if there are other applications like a mobile spectrometer. Definitely, that would be possible. Then I think a question for you, Muriel, as well about the broadness, and you showed that really nicely. Why is that so important to record 60 wave number at once?
I would like just to respond, I would like just give an example. We are interested in my lab by line mixing effects. Such effect can occur between two lines very close, but sometimes these two lines are not so close, and the distance between two lines can reach maybe 20 wave numbers. In this case, such spectroscopy is needed, really, because if you have to consider simultaneously the record of two lines separated of, for example, 17 wave numbers, with a QCL, with a diode laser spectrometer, it's just impossible. And but you have to obtain a very high resolution to be able to measure such effects as line mixing effects. Okay. So it is just an example, because with 60 wave number, we will be also able to study every Q branch for another example.
And another question which came in about a lot about the resolution, actually. Thank you for the excellent presentation. My question concerns the resolution. In the introduction, you said it was 0.0001, and then at the summary it was like 0.001. So just to make that clear, the first measurements which we did is now with the step sweeping. We got to the 0.001, so 10 to the minus 3. But there's no limitation actually that we get with the RSF1 also to high resolution. And that would be a question to you, Muriel. Would that be helpful? Is that important for applications?
Yes, yes.
High resolution?
We've talked about the fact that I hope that RSF1 can improve its resolution in the future. But I think that 10 to the minus 3 is enough for a lot of spectroscopic measurement. It will be very interesting also to improve the signal-to-noise ratio. And for that, we have just to consider a longer time of acquisition, and not so long, in fact, because with 10 minutes we obtain 500 as signal-to-noise ratio. If we consider, for example, 30 minutes or 1 hour, we will be able to improve considerably the signal-to-noise ratio. Thus, I hope that RSF will improve the resolution of the spectrometer for my instrument, but also for the next instrument. But I think that this value is enough for a lot of studies at high resolution. The signal-to-noise will be improved if the gas mixture is stable, if you have no chemical reaction, and if we make measurements in 1 hour or in 30 minutes, for example.
Okay. You mentioned once in an earlier discussion that time is also very important to acquire the gas. Can you give a little bit information why that is so important?
Yeah, for example, I given my my slide for my study devoted to a line intensity of formaldehyde. The problem is that if we wait several hours, as required with a Fourier transform spectroscopy, the pressure of the gas changes. If the pressure changes, it's impossible to make measurement because the line intensity and the collisional parameters as collisional broadening or shift depend directly on the pressure. Thus, we have to know precisely the pressure and we have to have a stable pressure, in fact. It's the reason why I make measurements on a few minutes. It's sometimes really required.
Okay. Thanks a lot. And there's another question out of the audience. I just read that right away. Great talk. Thank you. I must have missed this. My apologies. But what is the instrument line shape function coming from the RSF1? Is the line shape still impacted by typical interferogram transformation apodization effects? Ooh.
Yes, we have not for the first spectra recorded together. We have not yet measured the line shape. We are not sure that the line shapes Gaussian or Lorentzian or a void profile, but in a few days I will be able to taste and to say if the line shape of RSF1 is a Gaussian, a Lorentzian, or a void profile. But we have to work together, RSF and my team, to be sure that the line shape, I think the line shape is a Gaussian, but I'm not sure. Actually, I'm not sure.
As far as I know from the publication, it's the Gaussian.
Yeah.
Another question which came in, besides the scan speed, does IR sweep have an advantage in terms of brightness, optical power over daylight hedgehog or block engineer laser tuned spectrometers? If yes, what is the advantage and where it comes from? I assume that all IR instruments use the same IR QCL. Is that right? Probably it's referring, I just put that before in to that slide. As you can see, there's actually a big speed advantage of this dual-comb spectrometer RSF1. There's definitely also similar laser strengths, but RSF1 is the first spectrometer, a full spectrometer, which has actually also the detection unit, and we have a broadness of that 60 wave numbers. So you can have actually specific lasers. There's a laser pair, and like this, you're able to measure that fast with microsecond resolution. Let me see if I missed something here, or if we have another question. What is the signal to noise of methane spectrum recorded in Namur? And the duration of acquisition of the spectrum? I think that was, yeah, the question to you.
The duration was 10 minutes, and the spectra have been recorded not in Namur, in fact, but at RSF, but I presented, okay. And the thing that we have talked with my colleagues at RSF, and the signal-to-noise ratio is, I think, between 500 and 1000. They think 500, but I think that it's better.
Yeah.
And we have to.
I can back you up a little bit. I mean, you showed such measurements. They're exactly right. It's around 500, but we are very confident that this will be better. And just to come to an end, actually, I really want to thank you once again, because your inputs, without your inputs, I think it would not be possible to do those measurements. And I also want to thank the entire team of RSF, because we worked hard in the last few months during the lockdown. and we are very happy to present those data. I will not finish, just to also announce the next webinar, which we will have in a week, also same time, next Thursday, about rapid reaction monitoring of proteins with dual-comb spectroscopy. At that time, it will be more the speed measurements. So make sure that you sign up for that webinar together with Markus Mangold and Joachim Heberle. So thanks a lot for joining this excellent webinar. Thanks, Muriel, and have a good evening. All the best.
All the best.